So I'm going to start with going right back in time and just give you a bit of a feeling for how the Canterbury Plains were created, and that affects the hydrology of the Selwyn River and the whole zone. So if you imagine, and you might have to imagine hard here, that's the Canterbury foothills with the Southern Alps behind, and there are no Canterbury Plains. But we've got these big rivers, the Rakaia and the Waimakariri, coming out, fed from the big glaciers, and as they come out into the sea, they start forming these fans, alluvial fans, which, I'm sure many of you are familiar with seeing these types of fans in the mountains, that classic delta shape, and as they spread out, the water goes into various strands, and sometimes it's in a single channel, often it's braided. And then with time, those get bigger and spread further out into the sea until they're actually coalescing and they're coming together, and the Canterbury Plains are formed through these sorts of processes. But there's a big hole in the middle there, and it's in a place like that a river like the Selwyn flows down, the Waimakariri, coming out of the foothills. So it's not coming out of the main mountains, but out of the foothills and through this area between the fans, and it's bringing its own sediment and forming its own fan. But if you could imagine doing a cross-section across the Canterbury Plains through this area, and you think about the way that those are formed, then you end up with a topography that looks a bit like this, where you're saying essentially the Waimakariri and the Rakaia are raised higher than the Selwyn, which is in that lower place because of the way that those fans have formed. And that's quite important for some of the hydrology that goes on. So we've got this, and in fact you can see that if you look at a contour map of the Canterbury Plains. That's the 200-metre contour. And you can see that essentially this is higher on the Rakaia fan, and then it's going to the lower point further up the plains where the Selwyn is coming down here, and you've got the Hororata and the Waimakariri as well. And then it's going back up again to the Waimakariri Plains fan. So you've got this sort of topography, the plains aren't flat, is important. And then, so we've got these two big rivers, the Rakaia, and I've exaggerated this obviously, I'm just trying to demonstrate it, but, and I've drawn them like this deliberately, because if you take a river like the Rakaia or the Waimakariri, there's the flowing surface water, but there's also a lot of water in the shallow gravels. So it's actually moving water the whole time down over the surface, but then there's a lot of water just below the surface as well, which is also moving, but a bit slower, and it is moving. And as it's moving, it's also losing some of that water to deeper groundwater. Not all of it, but some of it will be, I say losing. I'm a surface water scientist, so I tend to think of it as losing. If you're a groundwater scientist, you think of it as gaining. But it's from the river itself, there is water moving down into the groundwater. And then you've got the Selwyn in one of these depressions flowing along. And it's the same issue, same thing. You've got water on the surface, if you're lucky, and you've also got water in the shallow gravels that's moving along just below the gravels. And it's also losing water down into the groundwater. But because it's a much smaller river, it's a lot less water that it's actually contributing to groundwater. If we then think about what's under the plains, this is quite a good illustration. I like to think about how the Canterbury Plains formed. This is the Rakaia River. When I gave this talk at lunchtime, I was saying, I always find it quite hard to work out which way the river's actually going in this case. Is it going that way or is it going this way? I'm pretty sure it's going that way. But the point about this is here you've got a braided river, which is the Rakaia, And if you start thinking about, this is what has laid down the Canterbury Plains. So the Canterbury Plains are like this all the way underneath, but without the rivers in them. And this is an important thing. There are no great rivers under the Canterbury Plains, but there is groundwater. And it is water that has filled the spaces that's been created in this way. And the reason I say this is if you take something like this little bit in here, it's an old channel, probably a few months before. The main channel might have been coming down here. If you walked up that, you probably find it'll have a lot of boulders and things. And if you come over into maybe an area over here, it'll be finer silts and things. And it all gets overlain on top of each other. So what you end up with under the plains is these pockets, essentially, which can be quite long. They could be up to even 1 kilometre long, where the water will sit and will move really quickly, but it's not continuous. It's not, that reaches a point and then it stops, essentially, or it goes much slower. So it's not a continuous river under the plains. It's these little bits where it can move a bit quicker at different depths, and that's what we see in the groundwater system under the plains. And if we think about those plains again, and this time if we do a cross-section down the plains, you end up with something like this. And it's not a coincidence that State Highway 1 is at this break point. What we see is the plains are much steeper further up, and then they flatten off as we get towards the coast. And State Highway 1 is at about the place where it flattens off. And you've got groundwater under the plains. This is a very crude representation. You've got this groundwater under the plains, which is in these little channels that sort of connect and moving their way, and they are moving. There's a gradient on that groundwater. Water moves downhill. It's moving as it comes down the plains. And it reaches this point where the gradient starts flattening off. And if you think about what that means, it's moving quite quickly and then it slows down. So the water has to go somewhere if it's slowing down. It starts filling up higher and filling up the pores above. It just makes sense. If it's going quickly and it slows down, you've got all this water still coming down, it'll start filling up the pores. And what you end up with is this water actually starting to come out at the surface. And that's where we see our springs and our spring-fed streams are where the groundwater is coming up close to the surface, and it's coming up. It's under pressure, and it's coming up as springs. So this is a representation of the Canterbury Plains. It's actually showing Christchurch, but it's not that dissimilar on this side of Banks Peninsula, where you've got this situation, as I've shown, where the water is flowing underground, and then a sort of an added complication, I suppose, that I didn't show in the last diagram, is that towards the coast, you've got these areas where essentially it wasn't gravel plains or shingle fans that were forming. It was swamps and shallow coastal deposits that are much finer sediments. And you get these lenses that you can see in here, and which are confining the water as it gets close to the coast. So the water is moving down, and then it's getting into these confined areas, but it is still breaking through in places, and we get the spring-fed streams. And then just, I guess, the other things to note on this is I've talked about the river losses to the aquifer. There's also a significant amount of land surface recharge. So this is the rainfall falling mainly on the plains, and it's infiltrating through and reaching the groundwater. And I'm going to talk about some of this sort of budget of where, how much there is of these different things. And of course, we've got groundwater abstraction, which is predominantly for irrigation, but not only for irrigation, it's also used for municipal supply and other things as well. So that's kind of what it looks like. And what that means on the surface is we have these sort of three zones where in the foothills it's higher rainfall, 16 to 1700 millimetres of rain, and we've got continually flowing streams and rivers. So the Selwyn at White Cliffs is always flowing. The Hororata as it comes out and the Waimakariri are flowing as well. And then in the middle of the plains, you've got lower rainfall, intermittent streams, they're flowing occasionally. And then at the base, we've got lower rainfall again, but we've got continually flowing streams because of this re-emergent groundwater. So that's the kind of the overall system. And I'll just think a bit about, I'm not going to talk about the upper reaches and the foothills. I'm going to concentrate more across the plains and in the lower reaches. And if we think here, we're looking at a mid-reach part of the Selwyn. And of course, the name of the Selwyn, the Ngaitahu name, is Waimakariri, which means river of stones. Much nicer name than intermittent stream. River of stones, which gives us an indication that actually it's always gone dry in the middle reaches across the plains. It will often flow, but it has always gone dry. We do know that. So we've got these intermittent reaches, and we can plot this up in one way. And what this is this end here is White Cliffs Recorder, and this is distanced going down across the plains. And the lines are showing us the percentage of time that it is flowing. And then the three colours, the black one is an average, just sort of in a normal year, and then the red is in a wet time, and the pink is in a drier time. So what we're seeing is as we come down across the plains, it starts losing, and in fact it goes dry for quite a lot of the time. So in a normal year, 40% of the year, it's dry as it comes across. And in this case, this is around Hororata, that sort of place, around that sort of area. But then you've got this slightly odd thing that in the middle, it suddenly pops up again. And it's actually flowing a lot of the time. And that's where the Hororata and the Selwyn come in together. And at that confluence, it's actually generally flows, well, it flows a lot more of the time, not all the time. And then it goes, so it's flowing less again until it pops out at the bottom, just somewhere above Chamberlain's Ford, where it's flowing most of the time. So that kind of gives us an idea. Now that bit in the middle is an interesting thing, because what we see is here's the Selwyn coming down, and here's the Hororata. And actually, I talked about those fans, having a gradient coming down. So there is a groundwater gradient heading in this direction, and you actually get springs, a lot of springs in this area. So if you know the Hororata, just around Mitchell's Road, this is Mitchell's Road here, and in this area here, there are a lot of springs, and it's a great habitat for Canterbury mudfish, and because there's permanent flowing water. But one of the interesting things is, where's that water come from? And you can't say exactly, but actually, a lot of it is the water that's lost from the Selwyn as it comes down, and there's a gradient coming this way, and it flows in a shallow groundwater across here, and it pops up in springs. So actually, the Hororata is a lot of Selwyn water as it flows down in this area. And it's down here that I said is that place where it's flowing a lot of the time in the middle. So that's just a sort of interesting little thing about the Selwyn, but it's linked into those fans and the way the Selwyn flows down across the middle of those. So I've talked about the intermittent reaches. What about the lower reaches? Here we go, on a good day. Coes Ford, plenty of water in it, and it has permanent flow. If you came to the lecture a couple of weeks ago that Ken Taylor gave, you will have seen this diagram already. This is the annual low flow at Coes Ford since the recorder went in 1985. So this is the lowest flow recorded at Coes Ford in those years. And in fact, when Ken and I put this together, we lied a bit because I wanted to show that we did have data for 2017, so I actually put a little bit in there, but it was 0. So it should really be 0 there because Coes Ford stopped flowing. It didn't dry up, but it stopped flowing. So that was just to show that there's data there. So when you look at a diagram, when I look at a diagram like that, there are two things that strike me about that. The first, when I'm being nice and optimistic, is, gee, there's a lot of variability there. That it's highly variable. Some years, the lowest flow is up to 1,000 litres a second, which is a QMEC. Sometimes, well, it's obviously down to 0, but at other times it's right down below 400 litres a second. That's the first thing, the variability. But I'm sure most of you have looked at that and you've seen the other thing about it, which is the decline, that we're seeing with time much lower low flows in the Selwyn at Coes Ford. So what's happened to those lower Selwyn flows? This is taken from a paper in the Journal of Hydrology, New Zealand, and it's showing the flow at White Cliffs and the flow at Coes Ford, and it's actually the 90-day annual minimum flows. White Cliffs is this line, and Coes Ford is the black line. Don't worry about the dashed line at the moment, just concentrate on those two. This is Coes Ford, this is White Cliffs. And the thing about this, again, you've got variability, we expect to see that, but the real thing about it is that with time, those are getting wider and wider, further and further apart. So this is going until 2006. This piece of work is being updated at the moment, and we're expecting to see that is continuing, that widening gap. And this was something that has been known about for a while. I'm looking at someone in the audience who did some of this work in the mid-2000s that was showing this discrepancy between the two, this widening gap. Now the dashed line is the land surface recharge. So that's the rainfall that actually gets through the soil and into the groundwater. And what you can see if you're looking at the dashed line is there does seem to be some kind of decline. It does seem to be getting less. And that lines up with what we know when we analyse, for instance, the rainfall at Christchurch Airport. It has shown a decline with time. That's the sort of thing that's being predicted in climate change scenarios. And maybe we are starting to see a bit of a decline, but it's not a lot. It's not enough to cause that discrepancy between Coes Ford and White Cliffs. So there's some evidence that we're going, right, well, it doesn't seem to be, land surface recharge has got a bit less, but it's not that much less, that there must be something else. And here's another piece of evidence. This is for Harts Creek. A very similar type of analysis, but in this case, it's using a model, and it's 2 runs of the model. The light blue line takes the model and looks at the discharge in Harts Creek being further around on Te Wahora, Lake Ellesmere, further south, and it's modelling it as a natural flow. So as if there was no obstructions of groundwater across the Canterbury Plains. And that sort of orangey brown colour, that's modelled with abstractions. And again, you can see the gap is getting wider and wider with time. So the effect of those abstractions is getting more as we go through time. And in this case, this is going up to 2009. So this is reasonably old data, but it just demonstrates this understanding that we're starting to get, that there's something here that's causing it. If we look at the overall water budget for the Selwyn, and this is a water budget for the groundwater, this is the type of average conditions that you see. So the inflows, in this case I'm changing to be a groundwater scientist, and I'm saying the inflows to groundwater, about 60% or a little bit more comes from land surface recharge. That's the rain, I can't say it again, the rain on the plains, infiltrating through. So about 60%. So that's big. That's a lot of water. And about 35% is coming from river recharge, from the Rakaia, from the Waimakariri, from the Selwyn itself, as it flows across the plains. And then you've got the stockwater race losses, which really are just the same thing as river losses. It's just that they've been channeled in a different way. So we've got some that's coming from stockwater. And then if you go to the other side and you say, well, this is a bucket, what comes in kind of has to go out. And this is what it looks like. We've got about 30% is flowing down through the lowland streams, through Harts Creek, the Lower Selwyn, Dawston Drain, the Halsall River, about 30%. This outflow to other zones, this is a bit of an artefact of this analysis, which was when one of the zones was the Lower Rakaia, and it's kind of now we think of it as all the same, so just kind of ignore that in a way. It's really just part of the overall system. Groundwater abstraction being about 30%, and then you've got coastal discharge. Now that's a guess, because we have no idea, because you can't measure it, how much is actually going out through springs and popping up out to sea as freshwater springs. And in the lake itself, we've got these freshwater springs. So we've actually calculated that as the residual, what's left, having measured these other things. Now, there's a couple of things I'd just draw your attention to on this. That the groundwater abstraction is sort of similar to the river recharge. But more to the point, the land surface recharge is about twice as much as the groundwater abstraction. And that's deliberate, because in setting the amount of water that could be abstracted, the rough rule of thumb method that was used was to say about half of the land surface recharge could be allocated as groundwater for abstraction. So the principle behind that is saying, this is a big system, it kind of has unders and overs through the year. If we allocate half of that rainfall, you've still got this significant amount of river recharge going on that's still feeding the system, and that we think the buffering capacity of that groundwater should be enough that about half is available for groundwater abstraction. So, land surface recharge, let's just look at that for a minute, because this is the average. This is over a long time period. If we start looking at that land surface recharge with time, and this is using an index method, don't get hung up on what the vertical axes are. And the difference between the blue and the orange, again, don't worry too much. The blue is actually rainfall and the orange is recharge. And it's in an index, so they look pretty similar. So don't worry too much about that. The main point is, look how variable it is. So I told you an average is 60%, but it varies all the time, every year. So, 1 year it'll be a certain amount, volume, and then another year it will be a lot less or a lot more. And you can see things that we're pretty familiar with. If you've been in the district a while, you know that in the mid to late 70s it was pretty wet. I made the comment at lunchtime that the famous picture of Fran Cotton playing rugby in the 1977 Lions tour, it was wet. He's covered in mud. And I think it was Lancaster Park. It was really wet in the mid-70s, but the early 70s were actually very dry. And you can see there's this variability. And you can again see what I was showing before about the land surface recharge, that there does seem to have been some decline with time, so there is less. It's probably exaggerated by starting this in the early 70s when it was very wet. But when we've done some statistical analysis, there has been a decline in the amount of land surface recharge. But the real point I'm trying to make here is look how variable it is. So year on year, it varies tremendously. So we come to the pachyderm, or the elephant in the room, as to what's this other bit that I haven't really talked about, and that's the groundwater abstraction. So this is modelled data, and it's modelled because we don't have records that go back to the early 80s. And, again, there are two things that I see when I look at that. One is it does vary, so season on season. A wet season, there's less irrigation demand, it varies. But the real point that you see there is this big increase through the 90s and into the early 2000s. And the amount of abstraction has increased hugely in that time. So what do we know about the water budget summary? Well, how do we summarise that? I've talked about this. The land surface recharge is the largest input, but we know that it varies year on year. And then some of those other things that I've already talked about. And the groundwater abstraction has increased markedly. So what does that mean if you go back to the budget? Well, this is a bit of a false representation because it was percentages, and I sort of hate to do this in many ways, but it's just for demonstration. Of course, in a dry year, you've got a lot less input, so that's why I've just tried to shrink that down. And then if you were to kind of say, well, what does that do? Well, in terms of the land, you're going to have a lot less land surface recharge. Now, this is a percentage, so it kind of makes the river recharge go up as a percentage. But the actual amount of water going into the system is a lot less. And as a result, what gets squeezed? Well, it's the lowland streams, by and large, that take that, and they start flowing at a lot less. So in a year when there's low land surface recharge, or probably more to the point, in the following years, not necessarily the same year, the lowland streams start declining. So the picture that I'm trying to paint here is that we've got a water budget. Land surface recharge is the biggest part of it. That varies year on year. When it's really low, irrigation abstraction starts having an effect on our lowland streams. And we know that, and we've known it for a long time. So the question really is, what's being done about it? What's the, having this information, what is it that we're doing about it? And I say we in the broadest sense. I don't just mean Environment Canterbury. I mean we, the community that live in this catchment. Well, the first thing is the kind of immediate over the summer. So when it's really dry, when the river's really low, what happens? And there are restrictions on the surface water takes. So it reaches a point with the river and nobody can take water anymore. And that also applies to groundwater abstractions that are close to the river. And that's what we call them as being hydraulically linked, or they're sometimes referred to as stream depletion or stream depleters. So it's part of that shallow, I said about the river is flowing through the shallow gravels as well. They're taking from some of that, and even a little bit further away where their abstraction is affecting the river directly. So if we look at the last year, so this is the Selwyn at Coes Ford for the past 12 months, going back to July 2016, what you can see is that all through the summer, this dashed line is the irrigation restriction. That's where everybody has to shut off who's taking water from the Selwyn River directly, or these groundwater depleters. So there was no irrigation taken all last summer, and this is through till April, when whichever of those, was it Cyclone Davie or Cyclone Cook? Cyclone Cook, I think. Well, the second one was when it reconnected and water came through. So in the immediate, during this dry period, you've got the surface water is being protected. The picture I painted is that the overall groundwater is also affecting this. So we've got to think longer term and think about the bigger picture of the groundwater abstraction. And what we know and what we've seen is that it's over-allocated. We know that there is too much groundwater abstraction in this area. So we've got the Selwyn Waihora Land and Water Plan, which has put an absolute limit on the abstractions. The first thing that it's actually done is it said groundwater and surface water are the same. And it's just put them together into a single pot, and it said we're going to treat them the same. And it's put an absolute limit, and that limit is about 30% below the current allocation. So that's acknowledging that it's over-allocated, and we need to get about 30% back. So the first question you may ask, is, well, how do you get the water back? Well, the first thing is, any transfer of a water consent within the catchment, you have to give 50% of it back. So you can sell your water consent to somebody nearby, but in doing so, you've got to give 50% of it back. And by back, I mean your allocation gets cut in half, and it's back to the environment. So that's one way that with time, we're expecting to see the amount of water allocated come down with time. The second thing is Central Plains water, and I'll try and explain a bit more about Central Plains water, because Central Plains is pivotal to this getting water back into our lowland streams. If you are a shareholder with Central Plains, you cannot transfer your water consent. So what I mean by that is, if you've got a groundwater consent, and generally these are up at the moment in the Tiparita area and up towards Hororata, and you have been using groundwater, and you take on using Central Plains water, you can't transfer that consent. So that's one thing. And this is all about trying to get it so that there is less groundwater being used in the upper catchment. And the Central Plains surface water is replacing those upper plains abstractions. Now, this is Central Plains. So this is State Highway 1, and the Selwyn is coming down through here. So the first stage of Central Plains is this area here. So this is the Tiparita area. Stage 2, which comes on in 2018, is this area over here. In this area, stage 1 has resulted in approximately, and it is approximate, we don't know for absolutely certain, about 60 million cubic metres of water that was allocated as groundwater and was being used by people by groundwater is now they're using surface water. So that is staying in the ground and moving down through the plains and available for the spring-fed streams. 60 million metres cubed water. It's really easy to make these numbers sound huge. I could put it in litres, or as somebody suggested to me once, why don't you talk in teaspoons? Then you'd be in billions and trillions of it. How much is that? Well, 60 million metres cubed, if you calculate it through and put it into metres cubed per second, is 1.9 metres cubed per second over the whole year. And it's not an unreasonable thing to put it over the whole year, because groundwater is a slow-moving system, and it will release it slowly with time. 1.9 metres cubed per second, or 1,900 litres a second. That may or may not mean something to you. Put it back into the Selwyn context. That minimum flow that I showed, that dashed red line, was 500 litres a second. So if you were to imagine that some of this water, now it won't be all of it, found its way into the Selwyn, and let's say it was 200 litres a second or something, which is a small amount compared to this, that's adding a lot of water into the Selwyn. If you go the other way and you think, where's that water come from? It's come from the Rakaia system, and it's been stored in Lake Coleridge, and it's being released down through the Rakaia. 1.9 cumex, when the Rakaia is flowing at a low rate, it's flowing at between 90 and 100 cumex. So 2 cumex is a small amount out of the Rakaia, and again, we're talking over the whole year. But it's a huge amount if it's going down through the groundwater and into our lowland streams. So it's a significant amount of water that has already been released, and with stage 2, when that comes on stream, we're expecting to see more again. And the real thing is that will be the real benefit to the Selwyn. At the moment, this is flowing down more towards Harts Creek. It takes a while for it to adjust. It's been such dry times that we haven't seen the results in those lowland streams yet. But given a bit more rain and more usual conditions, we would expect to see a significant amount of water reaching those lowland streams. So what's being done about it in the long term? More water in the lower plains streams. That was a key component of the Land and Water Plan. So the Zone Committee, that Alan's the chair of, set out as one of their key things was to get more water in those lowland streams, because it was known that they were under pressure. They were, the ecological health of them wasn't good, the flow wasn't good, and we needed to get more water into them. So that's happening through this unused groundwater, and I talked about the Selwyn main effect after stage 2. The other thing that's happening is that the minimum flow, so that line that I showed, that dashed line at 500 litres a second, is being raised. So that's the point at which people can have to stop abstracting directly from the river. That's being raised so that there will be more water left in the stream. And then the last thing, which is really quite a short-term sort of solution, is some of this possible augmentation that you may have heard about, which is about taking some of the unused water from Central Plains race, putting it into the groundwater or the near river in the upper Selwyn as it comes across near Hororata, and that would essentially augment a stream like the river, like the Selwyn. But that's relatively short-term. That's not a long-term solution. That's just something to kind of give a bit of a boost. The long-term stuff is about raising minimum flows, this unused groundwater from Central Plains. And that's pretty much what I wanted to say. Except, I've got that deliberately, which was to kind of illustrate that the water is coming. It's coming, it's coming, it's coming. It's not here yet. That's why we've seen such a catastrophic summer after these low recharge winters. But it is on its way. There already has been groundwater that's not being used, and it's on its way through the system. This was actually taken during the flood wave that came down the Selwyn. I'll just show you, because I find this really interesting, but you might not. I'll show you some things. This is, if you remember, this is Cyclone Davie, and then, if I've got them the right way around, Cyclone Cook, the second one. The red line is White Cliffs, the flow at White Cliffs, and the blue line is the flow at Coes Ford. So here we've got, and these are on the same scale, so we've got the flow at White Cliffs was about somewhere around 60 cumex. That's a lot of water. 60 cumex in the Selwyn is a lot of water. It's not a massive flood, I mean, we've had much bigger than that, but it's a lot of water. And yet, didn't cause anything down at Coes Ford. Didn't get there. And in fact, it didn't get there until 9 or so days later when the second event occurred from the second large amount of rain. And then this is just showing the same thing, except in this case the green is actually a shallow groundwater bore at State Highway 1. So what that's telling us is the water got to State Highway 1 because it shot up, but it didn't get down to Coes Ford. So one Friday afternoon, I went out and looked for this huge flood wave coming down the Selwyn to see what it looked like. And this is what it looks like. Frightening. This is the front of the flood wave. It's just percolating through into those dry gravels. And you can just see a bit of water there, and you're looking back up. I then walked about 100 metres up the stream, and that's what it was flowing at, just upstream. So it was quite amazing that you had this, and then this is just another thing where the flood wave was coming, 5:30, a couple of minutes later, it looked like that. And then 20 minutes or half an hour later, it was flowing like that. And you can see it goes down. And in fact, it got no further than that. It just filled up that area that you can see at the bottom there, and it didn't get any further. So that's about 2 kilometres down from State Highway 1. And it didn't get, no, a bit further down than that. It didn't get down to Coes Ford. But and it was only 9 days later when you had even more flow coming down through that it actually reached and got all the way down. It takes a lot of water when it's dry to fill up all those gravels and then finally reach it through. And of course what happens then is it stays a lot wetter and it takes a much smaller event to reconnect across the Canterbury Plains. Anyway, I wasn't sure if I was going to show that or not, but I had plenty of time.